Aloha class. Today 4.5 linearization, a very important topic when we talk about calculus and going into like calculus 2 and calculus 3. It's something that is going to stick with us this year, and then you'll also learn it next year in calculus 2 when you go off into college, and maybe you are going crazy and you want to go a little AB to a little BC, okay, where we learn some of this in BC. We kind of take it up a notch. And kind of get after it in terms of BC. All right, topic 4.6, approximating values of a function using local linearity and linearization. Okay, there we go. Look at your understanding, objective, and knowledge, and let's hit it. All right, the goal of linearization is to approximate the new y value for a curve using a line, right? Using a curve can be tough, but using a line, easy peasy Japanesey, right? To use the method of linearization, we need three things. Number one, we need a function. Duh, okay? Number two, we need the derivative of the function. Some of you said I need to start writing a little neater, so here goes. Let's see how I can do. And three, we need what we call an easy attachment point. Attachment point. Okay? Really, it's just you find the equation of the tangent line. So if anything, you guys are probably going to really like this stuff because it's kind of a little bit of a review. We just add a little bit of a twist, and we just talk about it some more. You know, we talk about our feelings. All right, here we go. It says consider f of x equals the square root of x. We know that f of 4 equals 2, right? Because the square root of 4 is 2. It says how the heck can we find out what 4.1 is, right? There's one way we could do. We could take the square root of 4.1 and put it in our calculator, but calculators aren't allowed, right? So if calculators aren't allowed, what the heck am I going to do? Well, let's find the equation of a tangent line, right? We start the year with this. Okay, you guys all should be able to do this. We already know our x1 and our y1. And so all I have to do right now, right, because it says that x equals 4, that means our y1 is 2. So all I have to do now is find the slope, right? And slope means what, class? Derivative, right? So the derivative, and it's set up there, I have to be able to take the derivative as 1/2 x to the negative 1/2. If I'm going to do that at f prime of 4, of 4, that's going to be 1/2, and that'd be 4 to the negative 1/2, right? Which would be a square root of 4, which is 2, but it's in the bottom. So doing my math skills, I get 1/4. So we have our y minus 2 equals 1/4 times the quantity x minus 2, x minus 4, I'm sorry. And then I simplify that bad boy, and I get L of x. Ooh, you do a little fancy L of x. That means just linearization, approximation, is equal to 1/4 of x minus 4 plus 2. Boom. That's what we call linearization. Now, what the heck is all of this stuff talking about? Well, we hopefully know what the actual graph looks like, right, class? That would be the square root of x. Okay, and what we're doing is that 1, 2, 3, 4, boom. Where is my tangent line? Let's draw it. Let's get a little color coded. I'm going to make that blue, boom, and boom. Okay, if you look and were to zoom in crazy like that, it's pretty darn close to being right on top of each other, right? They're doing a little red and blue go Cubbies. Are they going to take on those Cardinals? I hope so. But here we go. So if we look right there, if I use the blue to approximate the red, it's going to be pretty darn close. Now, hit that pause button. Do you think the blue would be a over approximate or an under? Unpause. You probably said over because the blue is over, right? And if the blue is the approximation, right, that blue is L of x. Ooh, fancy L, fancy L. Okay, that's L of x. And if L of x is above, it's probably going to be an over approximation. Okay, it says B. The tangent line you found is approximately the same as f of x, as long as we're really super duper duper close to 4. Use your tangent line to approximate 4.1. So what they're asking us to do is find what L of 4.1 is, right? Because we're just going to find an approximation. So f of 4.1 is approximately equal to L of 4.1, which is equal to, why am I using that? And why am I using that? Hopefully you understand why. If not, ask me in class. Okay, this is why I like to leave that in parentheses. It kind of makes the math very okay. Right, class? Get a little bit like that. 0.1 would be 1/10. Got it all done right here. Do that math. I get 2.025. 5. And so what would we like to know? We would like to know, hey, how close is that to the actual value? Ooh, let's do color-coded and keep this legit, right? Because f is, right, I'm going to plug that in there. So it's the square root of 4.1. Let's see what we get if we put it into our calculator. 2.0248456 tree. Oh, snap. This red, the actual, is really close to the blue. It is actually 0.00015 units apart from each other. Okay, and remember, that would be above. Okay, that's how much it is above. So if you rounded that to, or truncated that to 3 decimal spots, it is the exact same. Pretty darn cool, if you ask moi. All right, let's keep rolling here, class. Remember, okay, we don't do any marginal costs in AP Calc anymore, so see you later, okay? But they're going to ask us some things here, and we're going to turn it from linearization to what we call differentials, okay? And it says, suppose a function has a point of tangency at 2, 12, right? It means we can find a derivative, okay? And they tell us that the change in dy dx, remember, dy over dx means the change in y over the change in x, right? Which is a slope, right? Rise over run. That all goes together. And the change in x was 0.5. By approximately how much would y change? Is this amount the actual change in y? Explain. All right, let's go ahead and check out this bad boy. They're telling me that dy dx is equal to 8. And then they say the change in your x was 0.5. And they're asking me, if the change in the x is 0.5, what the heck is the change in the y, right? And so what I do for that is all I have to do is multiply by a 0.5, and I get 8 times 0.5, which would be 4. So what we say in that case is when we change the x by 0.5, the y kind of jumps up quite a bit, right? It changes by 4. Now we need to remember that when I do this change in x by 0.5, change in y by 4, that is just an approximated, right? That's not the actual change in y. Why? Because when I do my dy dx, right, class, that's the slope of a tangent line. And right, we use tangent lines to help us approximate for curves. And so if I wanted the actual change in y, just look at the curve. But you know what? It's not always easy to deal with curves, thus we use lines. And so that thus brings up this aspect of what we call differentials, which if I tell you what the change in x is, I can tell you pretty much what the change in y is going to be. But remember, this is all approximated. And as long as I'm staying really, really close to the actual point of tangency, then I'm going to get a pretty darn good approximation of what's going on with an actual curve. And remember, lines are so much easier to deal with than curves. All right, we are interested in the amount of change. Okay, right? It's like a rate. Everything in calculus is about changing, right? How fast can I run? Okay? I have no idea what I just did or what it even meant. Okay? But we are interested in the amount of change there is in the y value. This is called a differential. Differential. And I don't know about you, but I love these types of problems. A differential allows us to, what allows us to do is treat the dy and dx in terms of the notion change in y over change in x. Right? We use this little fancy guy. You probably do it a little bit in physics, right? That and that mean the same exact thing. Finding a differential is simply finding a derivative using different notation. When y equals f of x, consider dy dx. All right, let's do that. Consider it. All right. I'll consider it. You want me to consider it? I will do that. So let's consider it. Let's say y equals f of x. Well, what does that mean? That means dy dx equals f prime of x, right? It's kind of a notation thing. And that means your change in y is going to be equal to the slope times the change in x, right? That's what I kind of just wanted you to get from that. And we must remember that dy is a very small change in y. And dx is a very small change in x. Okay, now let's do some problems and see how this works, right? Because whenever we use a problem to help us to explain it, it kind of just stays with us a little bit better. Okay, now example 3. Example 3, we're going to go with differentials right now, and it's going to say find the derivative using differentials. Okay, so that's just a little dy dx is equal to 15x squared minus 6x. So that means your change in y is going to be equal to that slope, right, times the change in x. Okay, booyah. It's just that. Well, how do we use that stuff? You're about to find out why. Okay, so where does this come up in AP Calculus, okay? It comes up in a problem like this where they actually give me a change in x and we have to find a change in y. Okay, so we're going to go ahead and find the derivative with respect to differentials. So we always want to use this notation dy dx. Okay, we're not going to use that y prime or anything, okay? Equals 5x to the fourth minus 12x squared. And then we're going to go ahead and we're going to say, hey, the change in y is equal to our slope, right, class, times our change in x. But guess what? They give me an x value and they give me the change in x. So we're going to be able to say what happens here. So we go a little 5 to the fourth minus 12, 2 squared, and then I'm going to multiply by that change in x, which is 0.001. I got an answer right here to make it easy peasy really fast, and I get an answer of 32. Well, what the heck does that mean? Okay, that means when x, and so this is the important part, okay? Okay, class? When x increases from 2 to 2, it's 0.1. So here, get rid of that zeros. I was going to say, I thought to 2.01. So I'm staying super duper close to 2. Okay, so when x increases from 2 to 2.01 on the curve, on the original curve, okay, because remember what we're trying to do is we're going to try to approximate what is happening with the y. Okay, cube the y value increases by approximately 0.0. What do I have? I have 0.32 units. Okay, so my guess is if my answer is that, I had a little bit bad notes right here, that should be 0.32. All right, so now let's really get into the nuts and bolts of what's going on. Approximations aren't exact, duh. Okay, duh. But what they do is they allow us in AP Calc, because curves are difficult to deal with. And also we like to give a tribute to the homies way back in the day, right? Dealing with curves was almost too difficult sometimes if we didn't have a calculator or whatnot. So what they used way back in the day is they always use lines to help approximate things. And what we are noticing is that if we know what the change in our x is going to be, right, we're able to find out what our change in y is going to be. And as long as we stay super close to the point of attachment, we say, okay, then we're going to get really good approximations. And they would use this stuff back in the day to help themselves out, build things, anything of that sort, because dealing with curves was very, very difficult. So example 5 helps us to understand what's going on. Okay, consider the function f pictured to the right. Here we're going to label our point c, comma, f of c. So let's go ahead and label that. That would be c. That would be f of c. Whoops, sorry. Okay, and draw the tangent line at that point. So the tangent line at that point, let's try to do a real accurate job right here because it will help us to really understand what's going on. Okay, there's our tangent line right there. Okay, it says move your change in x to the right of c. When the change in x is very small, we say that the change in x is equal to dx, or the differential of x. What is the x value of the new point? Okay, so we have a little dx here going on, right? We're going to make our change here, dx, okay? And that point would be, that value right there would be c plus our change in x, right, class? Okay, the actual change in y, which is delta y, is given by f of c plus dx minus f of c, right? So if I come up here, right, boo, I get f of c plus dx. So this little guy right here would be your change in your y, or delta y. Everyone follow me? And since that's on the curve and this is on the curve, this right here is your actual change in y, right, class? We will denote the approximate change in y with a dy, okay? So this right here, right, class? If you look right here, this is my approximated y value. That's the actual y value, right? So we kind of have something going on right here. Dot, 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 dot. Ooh, my dot, dot, dots. My pen's not working. You guys love this. I do not like it, but I'm going to have to finish this last little piece with my little face up. So if we go like this, dot, 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 right? And we go like this, dot, 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 that would be my dy, right? So if you notice, as long as I'm staying super duper close, right, to this value, right? I forgot, I got to use this. As long as I stay close in here and my change in x isn't getting too crazy, I'm going to get a pretty good approximation. But if I go all the way out to here, I mean, that's a pretty big error, we would say, right, class? And so the last little piece of notes we have on this one page is errors in the approximation. And it is simply the actual, whoops, boom, you guys know I get flustered on this when the actual change minus the approximated change, which is your delta y minus your dy. I'm going to try to fix this, and I will be right back. Okay, class, let's see if I got this thing fixed. Please tell me I do. Okay, we're going to go to this pen. Please work. Come on. Yes. All right, let's look back at example 1 in a different way, right? When we did this example earlier and we estimated the square root of 4.1 using the function f of x equals the square root of x, we did that using linearization, right? We did that fancy L guy, okay? But now we're going to use differentials. Well, if I use differentials, I'm going to call this function y equals the square root of x. And my first step is going to be to find the derivative. dy dx is equal to 1/2 x to the negative 1/2. And then remember, we're going to use differentials. We know what the change is, right? We want to use, we want to focus at x equals 4. Why? Because I know the square root of 4, right, class? Equals 1/2, that's your slope, x to the negative 1/2, and your change in x. So here we go. Hopefully it's going to make sense out of this when we do this guy, okay? So what I want to do is I want to find out what the heck is happening to y when I change the x, okay? And how am I going to change the x? Well, once again, we want to use the value, the point of attachment at x equals 4. Why? Because I know the square root of 4, right? And then I'm going to change it by 0.1, right? That's what the problem is asking us to do, is go from 4 to 4.1. So it's be an x change of 0.1, and that's going to tell me how much I'm going to change the y by. So I do my little math here. That'd be 1/2. That'd be another 1/2, so that would be 1/4, right, class? And then I'm going to multiply that by 0.1. Do the math on that bad boy, and I get an answer of 0.025. Therefore, most important statement with any of these guys, right? When x increases from 4 to 4.1 on the original graph, which is y equals the square root of x, the y increases, right? The y increases by approximately 0.025 units, okay? And then guess what? This is how I can kind of approximate this guy, okay? Since the square root of 4 is 2, okay, right? That 2 would be our y value, 4 would be our x value. Then we know that the square root of 4.1 is approximately equal to 2 plus 0.025, which is 2.025, which we did earlier by linearization, but this time we did it by using differentials. Now, what they asked me to finish this problem is find the error. And do we all remember how I find the error? It is the actual value, which is the square root of 4.1, minus the approximated value, which is 2.025. So yes, the only way you can do this is with the use of a calculator. And if you remember before, I gave you that approximation earlier, but if you put this just into your calculator, just like it looks, you get negative 0.0001543, blah, 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 blah. Okay? And that gives us the error. Okay? And that's how much I was off. Okay, why is it negative? Well, because remember my line was above. Okay? All right, now let's do it for one of my favorite problems. One of these problems you definitely want to make sure you're able to do, and that is, how the heck do I find the cube root of 29 without a calculator? Cube root of 29 without a calculator. Let's think about this guy. Well, I know the cube root of 27. So maybe, okay, well, what am I dealing with? I'm probably dealing with this cube root function, right, class? And I know the cube root of 27, and 27 is pretty close to 29. So that would be, right, class? That'd be my point of attachment. And it says, find an approximation, and then find the error in our approximation. Okay, so let's do this bad boy. Well, how would I do it? It says use differentials. So here we go. dy dx is equal to, the derivative would be 1/3 x to the negative 2/3. Ooh, okay. And then, I'm going to multiply that dx on both sides, right, class? Because I want my slope at the point of attachment, and I'm going to multiply it by my change in x. Now, I don't want to put a 29 in that x, because if I put a 29 in that x, I will need a calculator, and I don't want to use a calculator. I want to show off the skills, right? So I get 1/3, and then let's use 27, because I've always told you, you better take a root first, okay? And then I have a change in x. Well, 27, but I really want to do 29. I'm going to have to really think about this, right, class? So I want you to pause after I ask this next question, and I want you to take a thought for this, okay? I'm using 27, but I really want 29. So what would the change in x be? Hit pause. All right, 27. I'm really doing 29. So my change in x from 27 to 29 is a positive 2. Put a plus there so you remember that for the future, okay? So here we go. dy equals. All right, cube root of 27 is 3. And then if I square that 3, it'd be 1/3 times 1/9, right, class? And then I'm going to multiply that by 2. So what do we get? We get 1/27 times 2, which is 2/27. So if I change the x by 2, I'm going to have to change the y by 2/27. So let's make our cool little statement then. Therefore, okay, when x, here, let me get this beautifully stated, so we just keep on doing it. When x increases from 27 to 29 on my graph of y equals the cube root of x, y increases by approximately 2/27. Well, what the heck would that mean? That would mean the cube root of 29 is approximately equal to, well, the cube root of 27 was 3, so it'd be 3 plus my change in my y. Okay? And right, fancy way of writing that would be 3 and 2/27. And so let's go ahead and find that error over here. What's the error again, you class? It is the actual value, so you would have to use your calculator, minus the approximated value. And let's see how close we are. I got my answer right here. I get an answer of, didn't have it in my notes, class, so I got out my calculator, and I got 0.14639. So I don't know, that's just an okay approximation, right, class? All right, we're getting close to 25 minutes, so let's roll. Okay, the measure of a side of a square is found to be 15 centimeters. It's also found that students' measurement with this ruler could be off by 0.05 centimeters. So that could be a change, right, class? From the real measurement. Find the approximate change in computing the area of this square if the original side measurement was off. So we're going to pretend like we were off, even though you guys, no way you would ever be off. Let's draw a picture. It is a square. We'll call it a side of x. So we have a function, which would be a equals x squared. It's an a. It's going to freak some of you guys out. Right, we have a point. What would my point be? Well, it would be 15 comma 15 squared, which would be 15 comma 225. So if a side is 15, it's going to give me an area of 225 units squared. And then we have a change, right? We could be off by, what was it? It said 0.05 centimeters. So believe it or not, let's do a little calc. Okay, if you could be off by that much, how much could I be off by? And people do this to notice, how big do I need to make a certain area to fit something in it? Okay, to fit this box, fit this cube in it. Okay, so here we go. Let's go ahead and do this, and we're going to do it in regards to differentials. So we have a little dA, and we're going to do it with respect to x is equal to 2x. Right, class? We get a little dA if I'm doing differentials. Your change and your slope right there times dx. And what are we going to do this? We're going to do this for when x is 15, right? And our change could be 0.05. So if we're off on the sides by 0.05, how much would we be off in the area? And it'd be 1.5 units squared. In this case, they actually do give me units, so it'd be centimeters squared. So we should write a little statement. The approximate change in area is 1.5 centimeters squared if the student side measurement, sorry, I'm trying to beat that clock. Oh, I didn't. Measurement is 0.05 centimeters above the actual measurement. Done. Aloha. See ya later. Related rates, my second favorite topic in AP Calc is next. Get excited.